When we introduced the definition of a set, we just said that it was a collection of elements. Now, it is possible to have a set with no elements, and we call that the empty set. And there's two different ways of denoting the empty set, one of which just involves opening a set with a curly bracket and immediately closing the set with an opposite curly bracket. So we open the set and we close the set and we put no elements in. Or more commonly, we'll denote the empty set with a circle with a diagonal line through it, the set with no elements. So if I consider E to be the set of even integers and O to be the set of odd integers, then I think it's fairly clear to say there's no elements in both sets. There is no way I can find a number which is both an even integer and an odd integer at the same time. So the overlap of those two sets, E and O, or E intersection O, is an empty set. We can also define a set difference of two sets, so a difference B to be the set of all elements which are in A but not in B. So I can also write that, for example, as A intersection B complement, or I can write that here as the set of all elements X such that X belongs to A and X does not belong to B. So if I take an example here, and I'm deliberately going to mix numerical and non-numerical elements. So the set A contains C, D, 7, and 11. And the set B contains C, 10, and 11. Then A difference B is everything in A which is not in B. So I have to remove C from A because that's in B. D stays, 7 stays, but 11 is removed because 11 is in B. So the only two elements which are in A but not B are D and 7. And going the other way round, B difference A, 10 is the only element which is in B but not A. And note that I haven't just written that B difference A equals 10, because 10 is an element. B difference A is a set. So B difference A is the set containing one element, the number 10. So I've opened a set, I've put the number 10 in it, I've closed the set. We say that a set A is a subset of a set B, and we write that as A subset B, if the statement X belongs to A implies that X belongs to B. So every time we know the element is in A, we know it must always be in B as well. So what we can say from that is that if A is a subset of B, then A intersection B complement has to be empty. So which elements are in A and not in B? There aren't any. There are many everyday linguistic examples of this. So I say that the set of humans is a subset of the set of mammals. Because, for example, as well, which humans are not mammals? None of them. The set of humans and not mammals is an empty set. Every human is a mammal. Also, if I've got two sets which are both subsets of each other, A is a subset of B and B is a subset of A, then I know that every element in A is also in B, and I also know that every element of B is also in A. Then A and B must be an identical set of elements, so I can say the two sets are equal, and hence A equals B. Now, we will sometimes see the definition of a strict subset, and we say that a subset is strict, and you can see the notation is slightly different. It doesn't have the bar on the bottom of the subset notation. So I would say that A is a strict subset of B if A is a subset of B, but A does not equal B. So B is not a subset of A, but A is a subset of B, and that's a strict subset. So it doesn't matter what A is, everything is a subset of itself. So A is always a subset of A, whatever A is. By definition, everything in A is in A. But A is never a strict subset of itself.